Lesson 4.5. Find all zeros of polynomial functions. So let's use the rational zero theorem and synthetic division to find the zeros of a polynomial. So use the rational zero theorem to list all the rational zeros. Use synthetic division to test a possible zero. If the remainder is 0, it is a 0. You can use a graph on your calculator to find the x-intercepts to help choose what you're going to try. You repeat using the depressed polynomial for the next time around, and then that depressed polynomial for the next time around, until the depressed polynomial is quadratic. And then you can find the zeros of the quadratic by factoring or using the quadratic formula. So how many zeros, how many solutions should you be looking for? Fundamental theorem of algebra tells us. It says if we have a polynomial function, then there is at least one zero. Woohoo! There's one answer, at least. More specifically, it has the same number of zeros as its degree. So if the degree is 3, there are 3 zeros. If the degree is 5, there are 5 zeros. When we were doing quadratics, there was always 2. We might have gotten a double zero, but there's always 2 for quadratics. Cubics will always have 3 zeros, and so on. They just might be imaginary. Let's try an example. How many solutions does x to the fourth minus 5x cubed plus x minus 5 equals 0 have? And then find all the solutions. Well, we notice it's x to the fourth, so that means there are 4 solutions. It's just whatever the highest exponent, whatever the degree is, that is the number of solutions. Now, to find all the solutions, we can do the p's and q's, or we could try factoring. This one, I see it has a 1 and a negative 5, and a 1 and a negative 5, 4 terms. I can probably factor by grouping. Out of the first group, I can factor an x cubed, leaving the x minus 5. Out of the second group, I can't factor out anything, so let's just say we factor out a 1. Then the x minus 5 is the same, so we can factor that out, leaving the x cubed plus 1. Now, if we remember, a cubed plus b cubed, because 1 is the same as 1 cubed, is a plus b, a squared minus ab plus b squared. So that would be x plus 1, x squared, minus 1 times x, plus 1 squared. So then we can take each of those equal to 0, and get x equals 5, get x equals negative 1, and then we could try factoring this quadratic. However, when you get the quadratic out of factoring the sum of cubes, it's not going to be factorable, so we're going to have to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So this looks like we have 1 minus 4 is negative 3. Square root of negative 3. The square root of 3, and the square of the negative is I. And we would usually split this up into 2 separate fractions. And so there we have 4 answers. We have 5, negative 1, 1/2 plus the square root of 3 over 2i, and 1/2 minus the square root of 3 over 2i. Let's try another one. So we could try factoring this one. Yep, it's not factorable. There are 3 solutions though. So let's try, it doesn't look like a great one for factoring. All right, so let's do p's and q's. P's are, what factors a 10? So 1 times 10, 2 times 5. Q's are factors of leading coefficient. So our possible rational zeros would be 1 over 1, 2 over 1, 5 over 1, 10 over 1. 8 choices. And we're looking for 3 solutions, or 3 zeros. And again, 0 is simply the value of x that makes the function equal 0. All right, so let's pick something. Let's pull out the calculator again. Let's go back and put this one in. So it's x cubed minus 7x squared plus 16x minus 10. And let's look at the graph. We appear to have an x-intercept at 1. So let's try that for our synthetic division. Coefficients 1 from our function 1, negative 7, 16, negative 10. Bring down, multiply, add, multiply, add, multiply, add. Oh, look at that, we got a 0. It was x cubed, so now we are at x squared. That is quadratic. Try factoring it. The 10 could be negative 5 and negative 2. Wait, that does not give us the 6. So let's use the formula. All right, b is negative 6. A is 1, c is 10. So it's 6 plus and minus 36 minus 40. It's negative 4. So that is 6 plus and minus 2i. Split it up, so it'll be 6 over 2 plus and minus 2 over 2i, or 3 plus and minus I. So our answers are 1, 3 plus I, 3 minus I. 3 solutions, 3 zeros. Notice on our graph where it starts to come back towards the x-axis right here, that is where the 2 imaginary solutions are. One more theorem, the complex conjugate theorem. If the complex number a plus bi is a 0, then a minus bi is also a 0. So in other words, imaginary zeros come in pairs. Same is true for irrational, which means with square roots. They also come in pairs. If a plus the square root of b is a 0, then so is a minus the square root of b. Okay, let's write a function that has these zeros. So we're going to do that by just putting x minus each of the zeros. However, we have this imaginary 0, 4i. Its complex conjugate, so this would be like 0 plus 4i. 0 minus 4i, or just negative 4i, is also a 0 because the complex, or the imaginary zeros, come in pairs. So x minus negative 4i is x plus 4i. Then we multiply these together. It's easier if you multiply the imaginary ones first. So x squared, 4ix, negative 4ix, minus 16i squared. Combine like terms. Oh, those cancel out. And remember, I squared is negative 1. So negative 16 times negative 1 will make plus 16. Then multiply again. We'll have x times x squared, x times 16, negative 2 times x squared, negative 2 times 16. Rearrange it in order. And there you are. Polynomial function with those zeros.